Uh, just in case, if you check the Canvas announcements, I sent you one, I think, over the weekend about the quiz. So, your presentation, I think, is on Thursday. I'll usually try to make the quizzes just based on the material from last week, since last week we basically covered almost nothing. It's just like very basic stuff about like vector addition. If you just look at the top questions that I told you, it would be on. But you know, in general, like after this week, we will have covered a lot more. So like for next quiz next week, will be slightly more interesting. But yeah, for the one on Thursday, just basically those three questions that I posted on the Canvas announcement. And then the recitation, the workshop after the quiz. Again, that one is greater. I mean, to get all the points, you basically have to like participate on, like do it or participate on it, and it will be based on the dot product, which is essentially what I'm hoping to cover today. So the idea is that I still have to give you a few things about you know, properties of vectors, and after you know, like talk about these vectors I, J, K, which you may have heard of. And after we do that, then we can start talking about the dot product, which is where we'll spend the most time for today's class. So just to remind you what I was telling you last time. So if you think of a vector, you can think of a vector like as some sort of like arrow in space. So that means that it has a direction and a size. So okay. So vectors have directions and size. The size is also called the norm or the magnitude. And if you have like coordinates, like if you have like the XY plane, then you can always move. You can always move the vector so that it starts at the origin. So that's how it could look in that situation. And so say this is like the point x comma y. In that case, when you write something like b equals x comma y, when you write something like this, that you just mean like the vector that started at the origin and terminates at the point x, y. So this is like the, you know, we'll work a lot with vectors that have two entries. The other type of vector that we'll use a lot, most of the time, it's like vectors with three entries. So when you do like, when you draw a vector with three entries, and we'll talk more about this next time when we do the cross product, it's kind of the same. You just draw an arrow in space that starts at the origin, but now it just can terminate at a point that has coordinates x, y, and z. And so you would write something like b equals x, y, z. So these two are like the pictures you should be most familiar with for the course. Like, you know, theoretically, you could talk about vectors with 4 or 5 or 6 entries and so on, which are useful, but our class, basically all the vectors have 2 or 3 entries. But yeah, it's possible in you know, it's possible to have vectors with more entries. But not for us. So like an example where that's used, like is in statistics, or like just like where you're measuring properties of a population. So you could have like a vector of characteristics. So for example, like the first entry of the vector could be your height, the second vector could be your age, the third entry could be your weight, the fourth entry could be, you know, what other property you could have, like another numerical property. Well, your income, like, you know, you could have like a, you know, you're collecting data, and sometimes like the data will be arranged as like just like a list of numbers. So in that case, you could still talk about a vector. It's just that usually, you know, there are many properties you would like to analyze or sample, and then in that case, a vector would have several components. But for us, like, you know, most of like the intuition of what's going on, you can pretty much understand when the vectors have either 2 or 3 entries. So that's what we will do for this class. So the other thing that I didn't tell you last time is that if you have a vector, then you can rescale that vector. Well, which I kind of mentioned, but at least not in terms of giving you like a formula. So like you can multiply a vector. You can multiply a vector by a number. And again, numbers sometimes will be called scalars in this class. So how does that work? So if you wanted the vector, if you have a vector v, what should the vector 2 times v or 3v? Well, let's say I think this could look more like 2v. What should let me try to draw a nicer number 2. So what should like the vector 2v mean? It should mean like a vector that's twice as long, but it still points in the same direction. So this one is twice as long, but same direction. And then if you did something like negative a third of v, what does that mean? It means the third will means that you the length will be a third of it. And the minus just tells you that you reverse the direction. So whenever you multiply a vector by a negative, by a negative number, the effect is to just like reverse its direction. So this is a third of the size, but the opposite direction. And then you will reverse directions. That making sense? So, like any other number kind of works the same way. There's an extreme case, which is 0 times b. Okay, that's kind of worth pointing out. So what should 0b mean? Well, so essentially, because it's the number 0, you kind of collapse the vector to a point. That's the only case where the vector like doesn't really look like an arrow, it just looks like a point. And that's actually called the 0 vector. So this is called the 0 vector. So it has like 0 length basically. And in this case, since it's more like a point, it doesn't really point, like it has no direction, but that's fine. This is like the only situation where the vector like has no direction. So it would be no 0 length, no. And you don't try to define a direction. So the direction is undefined if you want to say it that way. Is that making sense? So it is a vector, it still can be confusing. It's not the number 0 because, for example, in this picture, it's like here's the 0 vector, but that means that it has 2 entries. It's just that both entries happen to be 0. Okay, so it's slightly different from the number 0. Or in this case, so with vectors with 3 entries, here's the 0 vector, it's literally located at the origin, but then it has 3 entries because again, now you're looking at vectors with 3 entries. So the 0 vector is still like a vector in the sense that it has multiple entries. It's just that all of their entries in this particular situation are just 0. So don't confuse the 0 vector with the number 0. In a sense, there's like a 0 vector for each for vectors of with a given number of entries. So there's a 0 vector for vectors with 2 entries. There's a 0 vector for vectors with 3 entries, a 0 vector for vector with 4 entries, and so on. Yes.
Is the 0 vector like by definition always at the origin, or is there a way to get like a 0 length vector?
Right. So you could move it around. And that's fine, like because like still the vectors can be moved around, but once you have like the coordinates, like yeah, like you kind of like are forcing the vectors to start at the origin. And if you're forcing all the vectors to start at the origin and this one has no length, then it kind of remains there. So yeah, in principle, it's just like the thing is like if you put it somewhere else, then it's just kind of like like a dot, which is fine. But if you just stick to the convention of drawing all the vectors so that they begin at the origin, there's just nowhere for the zero vector to go. But yeah, like if you forget about the coordinate system, then in a sense, like the zero vector could be anywhere. But for us, like, for the majority of the course, you kind of have like a fixed coordinate system in your mind. And then like the convention is this one. But no, that's good. Anyone else, any other questions about this? Okay, and then so before moving to the dot product, there are two more things that I wanted to tell you. So, when you look at vector like this, so when you look at a vector like this, you want to think of this vector like kind of as being made up of two pieces. One piece which is completely horizontal, which is this one, this yellow one, and another piece which is completely vertical. Okay, which is this green one. So there's a sense in which you can break apart like a vector into components, and I'll tell you in a second how that works more precisely. Okay, where one is like kind of parallel to the along the x-axis, and the other is along the y-axis, and there's something similar going on here, where say if you have like a vector like this, then there's going to be, this vector. If you have like a vector like this, then it has like a shadow on the plane. So you can draw like a shadow here, and then this shadow has still like these two pieces that I just drew here by like a version for this one. And then what makes this like a vector with three entries, and then it has like in addition to these two pieces, like a third one. So it would be a piece like this. Okay, and the thing is, like, those pieces are more easily expressed in terms of the vectors I, j, and k. So let me tell you what those vectors are. So those are the three, they're called the unit vectors, or like the standard unit vectors, because there are more unit vectors that we'll talk about later. So let me put them here. These are called the standard. So when it's on the XY plane, they're just I'll still call them I and J. So like the first one is I, which is a vector that goes from the origin to the point 1, 0, and the other one is called J, which is the vector that goes from the origin to the point 0, 1. Okay, and so what happens with these two vectors? So the idea is that they're mutually perpendicular. That's going to be important in a couple of minutes. So these two are mutually perpendicular, or just perpendicular. And then just say IJ are perpendicular. Okay, and then each has length 1. So each has. So because they have length 1, they're called unit vectors. So these are called, so they're called unit vectors. And then, well, as you can see from the picture, like this one is parallel to the x-axis, and this one is parallel to the y-axis, right? So parallel x-axis, and then this one is parallel to the y-axis. Okay, and then there's a version of these for the case when the vector has 3 entries, and again, those are like the two cases that we'll focus the most on. In this class. So when the vectors have 3 entries, you kind of have the same situation as before. So you have the vector I, it's just that now the vector I goes from the origin to 1, 0, comma 0. So you just have to add a third entry, in this case, to the vector. And then J goes from the origin to 0, 1, 0. And finally, K, like just to continue that the same colors that's there. The last one is called K. And this one is from the origin to 0, 0, 1. So in practice, usually when people talk about I and J, they refer to this version, but there's no confusion, like, the context would tell you whether you're thinking about like the vector with 2 entries or 3 entries. Like, so that's why like there's no like, like much of a problem in writing I for both cases, because like the only difference is that whether you put like an additional entry of 0 or not. But what is the idea with these vectors that again, if you look at it, actually they're they're right here. So if you look at any of these two vectors, like if you look at them in pairs, they're mutually perpendicular. So there's a 90-degree angle between these two, a 90-degree angle between these two, and a 90-degree angle between these two. So they're mutually perpendicular vectors. So and the other property is like again that each has length 1. So each has. That making sense? Questions about this? So why are they useful? Basically, they're useful because then any arbitrary vector can be decomposed in terms of these 3 vectors. I mean, kind of like it's the same story for the case with 2 entries and the case with 3 entries. I will just do it in the case with 3 entries because it's a little bit more like general to what we need. But so what I'm trying to say that say if you start with the vector, let's say you start with this orange vector, which is terminated at the point X, Y, Z. Okay, then what I'm claiming is that you kind of can break this vector into 3 pieces, which are the 3 pieces that I'm showing you in this picture. So how is a convenient way to break it? So the first piece is kind of all along the x-axis. So the first piece will keep track of x. So let me write it like this: x, comma 0, comma 0. The second piece is all aligned with the y-axis. So I'll just keep the y. And the last piece is all completely aligned with the z-axis. So I just keep the z here. Okay, and if you remember like how I told you last time to add up the vectors, how to add vectors, then this kind of makes sense because to add up vectors, you add the corresponding entries. If you do x plus 0 plus 0, you get x. If you do 0 plus y plus 0, you get y. And if you do 0 plus 0 plus z, you get c. So it's really the same vector. It's just like kind of, written in terms of like building blocks, and the building blocks are kind of like along the x, the y, and the z axis. Is that making sense? And then what is this vector? I mean, if you think about it, this is kind of like the vector I, but just rescale by a certain amount. What amount? The amount X. And then this is like the vector J, but rescale by a certain amount. What amount? The amount Y. And the same with this one. It's like the vector K, but made Z times bigger. So actually, what this ends up boiling to do is like X times 100 plus Y times 010 plus Z times 001. So that's another thing that's nice about multiplying a number by a vector, which I didn't say explicitly, but when you multiply a number by a vector, it's really just multiplying each entry by that number. So what I mean here is like multiply each entry by X, and that's how you get X 0. Multiply each entry here by Y, and that's how you get 0Y0, and then multiply each entry here by Z, and you get 0, 0, Z. Okay, but so what that tells you is that the vector V, which was XYZ. Well, that's just XI plus YJ plus ZK. So any vector can be written in terms of three pieces, and like it's just those three pieces are like related to the vectors I, J, and K. So this is like a decomposition of like V in terms of I, J, and K. I'm about just to, I'll try like an example in a second. The in terms of I, J, K. So like this is like, the point is that this is kind of like an alternative way to write a vector. So for example, just to give you two quick examples. So if someone writes like, oh, consider this vector 2i minus 3j plus 5k, what do they mean by that? They just mean the vector that goes from the origin to the point 2, -3, 5. Or if someone says like, oh, consider a vector with this I plus 3k, well, the number multiplying I is 1, the number multiplying j is 0, and the number multiplying k is 3. So, well, like this notation in terms of I, j, and k allows you just to, I mean, with that you can go back and forth between writing the vector in terms kind of like of the coordinates of the point where it terminated, or in terms of these uh, basic unit vectors. If someone has taken linear algebra, this is what's called like a linear combination. So this is saying that the vector V can be written as a combination of I, J, and K. And linear just because none of the variables are kind of being squared or cubed or raised to the power 1/2. It's kind of like the power that is being raised to is like 1. So it's like x to the 1, y to the 1, z to the 1, I think. So the coefficients are kind of like linear. That makes sense. So this is just like a way to, again, get used to. At this point, we're just getting used to like rewriting things in many different notations. Okay, the first, but now, like that I have said this in place, I can tell you about the dot product, which is like the really important thing that we have to discuss today. So, but you'll see this is actually something that will come in handy when we talk about the dot product. So, let me see how. Now we're going to talk about the dot product, which is also called dot product is how I'll call it in class, but sometimes it's also called the scalar product. So again, the idea is like to add vectors. To add vectors is kind of like the most naive thing you could do. You just add the corresponding entries. To multiply vectors, which is what we're going to try to do. That doesn't really work that well. So you could try to multiply vectors just by multiplying the entry. So like, let me just do something that doesn't work or is not interesting. So here's something that's not interesting. So like you could say, well, if I give you a vector. Okay, you could say, maybe I want to multiply them, right? Let me write it just, maybe you would like to say something like u times v. Maybe that would be the vector you get just by multiplying the entry, right? Something like that. So you would do 1 times 2 is 2, -1 times, let me put square root of 2 as well. Right, or something like that. So -1 times 1 is -1, and 2 times 3 is 6, right? So you could think of maybe that's like a multiplication. I mean, that kind of seems like something you could try, right? Since it actually doesn't like, it doesn't end up being as like useful in applications or other like things that you could be interested in. But there is an easy fix to this, which we'll see in a second. But just like multiplying them like that and producing a new vector, that's not it doesn't really give you anything that you would like to work with. Okay. Now, before writing the formula for the dot product, I should give you like this formula for the length of a vector. So let me also tell you that. So what is the length of a vector? Well, it's just basically the Pythagoras theorem. So say the vector by the way, there's no reason why the vectors are always, I mean, I'm just drawing them on the first quadrant because they just look nicer, but there's really, the vector can be anywhere. So the formula would still work just as well. So if you wanted to find the length of this vector, right, like you can draw like a right triangle here. The idea is that this side has length x and this other side has length y. And so the length, which last time I told you was also called the magnitude. Well, that gets written as absolute value, like the notation that you use for that is kind of like an absolute value notation. So you would write like absolute value of v. It's just like the square root of x squared plus y squared. Okay. And the other case that we would be interested in when you have like a vector with 3 anchors, because again, those are like the only two situations we'll really study in this class. Okay, so that one is a little bit more tricky, but if you have, I don't know if you have seen this one before, there's secretly like a right triangle here, which is easier to draw if you like with a concrete vector. So if you have like a vector like this, then like think of this as a hypotenuse, like one of the sides of the right triangle would be this vertical one, and then the other side would be this horizontal one. So there's actually like a right triangle here as well. Okay. Which is what I'm trying to denote here. So you can actually like apply like a Pythagoras theorem in this case as well. And like, I'll just write the formula for what you get. Okay. So the length of vectors is just like, just it's like the length of a hypotenuse is just like you square the entries, add them together, and then take the square root of that. And it doesn't matter, like, how many entries the vectors would have, like, there's kind of like a similar formula that works. So if it, like, the vector had like 4 entries, which again, we would not do, if it were like x, comma, y, comma, z, comma, w, then the length of that would be x squared plus y squared plus z squared plus w squared, and then you take the square root of that. So there's kind of like a formula that works in any of those situations. But again, like, our focus will be these 2 cases, and that will be enough for our purposes. Okay, so yeah, I just mentioned this first because this length will appear in the formula for the dot product, and it's just kind of like important to get used to the notation that for the length, you use kind of like an absolute value. So for example, just to get you used to the notation, so if I write something like absolute value of I, well, or absolute value of j or absolute value of k, that just means the length of the unit vectors I, j, and k. And since I told you they have length 1, then what I'm writing here is that should be equal to 1. So that's like what I mean. Or the length of the 0 vector would be 0, which also makes sense. Okay. And something like the length of the, just to put another one, what the length of a vector I plus 2j minus 3k. Well, that's the length of the vector 1 to negative 3. And that would be root of 1 squared plus 2 squared plus negative 3 squared. So that's what, like 10 for root of 14, whatever that is. Okay, so that so the point of these things is that it's always a number, right? Like the length is a number or it's a scalar. So this is always a scalar. This is a number. So that's why there are no arrows. Like once I compute what that is. Okay, so for the dot product, we need to know a little bit about the length. So like I just gave you a formula for the length of the vector. There's another thing that you need to know, which is the angle between vectors. So what's the angle between 2 vectors? We also need to talk about the angle between vectors. And so here's the idea. If you have 2 vectors, let's say I have this vector and this other vector, as I said, like, if you want to talk about the angle between them, it doesn't really work if the vectors are kind of in different locations. You should always move them first so that they start from the same point. Like, for example, here, like they're always starting from the origin. So you just bring them together so they start like from a common point. Once they have a common, like, they have a common point where they start from, then there is some obvious angle that you can see in here. The thing is that if you think about it, like there's like kind of like this angle, and then there's this smaller, there's this smaller angle, and then there's the complementary angle that you see. So there are actually like 2 options for what the angle should be, and the convention is just to choose like the one that's the smallest. So the angle between 2 vectors, like, how much can the angles be? So if the vectors are pointing in the same direction, the angle is 0. You start increasing and increasing and increasing until you get to 90 degrees, right? So there's like an angle of 90 degrees here. Increase, increase, increase until you get to 180, right? And if you keep increasing this, then it actually makes more sense to go down the other route. So it actually, you can always take it between 0 and 180 degrees. So, so what I'm trying to say is that if you have 2 vectors, U and V, by the angle between them, I mean the one that you see right here. So you choose this, you choose this angle. So the angle is going to be between 0 and 180 degrees, or between 0 and pi radians, whatever, however you prefer to call this. But so visually, if you wanted to find it out, you do have to put like the vectors so that they start from the same location. If that makes sense. Okay, but the convention is to take them so that it goes from 0 to 180. Okay, so now I can finally give you the formula for the dot product. So the dot product is going to be a way to multiply the vectors. So let me see if I see this one. So what is going to be the dot product? So you're going to be given two vectors u and v. So there's an angle between them because of what we just discussed. So the idea is that the dot product of u and v. So it's called dot product because in the notation, literally you'll see like a dot between them. So this is going to be the dot product. And by definition, or like the formula, is going to be that this equals the product of the lengths of the vector. So you find the length of u, you find the length of v, and okay, so here's the thing, and I'll explain why you do this in a second, but so the dot product multiplies the lengths of the vectors, but it also multiplies it times the cosine of the angle between them. So that's like the important thing in the dot product. So the product of the length times the cosine of the angle. Okay. So let me give you just a quick example and then I'll explain why it's defined this way. So just to do something very basic, say, here's an example. Let's say that u is like the vector 2, 0. Let's say v is the vector 1, 1. Okay. So what would be the dot product between u and v? So it would be the length of u, so like the length of u times the length of v times the cosine of the angle between them, right? So there's this angle between these two vectors. You want to multiply by that cosine. So, well, what's the length of u? That's just 2, right? What's the length of v? It's just square root of 2. So it's just square root of 2 because of the Pythagoras theorem, right? And what's the angle between the two? Then it's also, I mean, it's the angle between v and u is the same as the angle between v and the x-axis. That's kind of, I chose it so that it would be easy to see. So this is like an isosceles triangle, if you think about it. And so the angle should just be 45 degrees, if that makes sense. So theta is actually 45 degrees or pi over 4, right? So you're multiplying times the cosine of pi over 4. I mean, there are different ways to write that, but it's 1 over root of 2. So you get 2 times root of 2 times 1 over root of 2. So you just get 2 in this case. So the dot product in this case, whatever the meaning is just 2. Yeah.
Which two sides are equal?
You know, if you draw that you have like a right triangle here for V. So you know, because this is the point 1, 1, the height is 1 and the horizontal side is 1.
Always.
Yeah. So I meant that. So the angle between V and U is the same as between the V and the x-axis, but to find that angle, it's just like, you know, like you basic, like, you know, you do the trick thing for V. Okay, any other, yeah.
So like the example you had at the very beginning,
Mhm.
where you could like the non-existing
Uh-huh.
way, multiply them, is that like wrong? Or just like not mathematically useful?
No, so it is not wrong, it's just not as useful, but actually that one can be fixed in a second and it will be related to the dot product. So you'll see like it actually is not unrelated to the dot product, but there's a fix that needs to be made. But yeah, I'm just trying to say it's like, you know, when you start thinking about how to do these formulas, it's not super obvious like what ends up working or not, right? So I'm trying to say like, yeah, so definition, like it's something you could definitely try. It's just, it doesn't like have like the same applications, say, as like, for example, the dot product. Which I'm about to give you like the first application in a second, but I think someone else, yes.
Right, could you see why the third side, like in particular lines that,
Could I explain this one?
no, the line drawn from one V to.
This line?
Yeah.
Oh, the thing is like, let me just draw it, let's ignore the vector U because I think that can be what's creating the confusion. So if you just draw the vector V, right? If you draw the vector V, if I write it as 1, 1, right? That means that the x coordinate is 1 and the y coordinate is y as well. So, you know, I could draw it like, just to emphasize that a little bit better. That's what that means. And so because of that, like these two sides are the same, right? So it's just a isosceles triangle. And that's how you get the 45 degrees. Is that better?
So the U vector, we don't list.
In this case, like the only important thing of the U vector was that it had the same direction as the x-axis, and that's why the angle coins, like, you know, asking for the angle between V and U is kind of like the same as asking between the angle between V and the x-axis. But yeah, that's the only importance that the U vector plays in that case. No, good. Anyone else? Okay, so like the first question is like, so why do you define the dot product in this way? Before I tell you that, just notice that it's actually, this does come as a number, right? So the point of the dot product is that this quantity will be a number. So you start with two vectors, but you get a number. So like this is an actual number. So not a vector. That's just important to distinguish it because next time, the next class, we'll talk about the cross product. And that one will produce a vector, not a number. So whenever you take the dot product between two vectors, the answer has to be a number. So that's not the first important thing to know. So there are two big uses. There are two big reasons why the dot product is useful. But this one is probably the most important one. So like why this definition? Because what happens is the vectors happen to be perpendicular. Right, so let's say that the vectors happen to be perpendicular. Oh, we know that the cosine of 90 is 0, right? So cosine of 90 degrees is 0. So the dot product for two perpendicular vectors, just from the fact that this becomes 0, it doesn't matter what these two other factors are, 0 times anything will become 0. So the point is that for perpendicular vectors, the dot product is 0. So that's kind of the main reason why you care about the dot product. So this dot product is 0 for perpendicular vectors. In fact, just to like, it's kind of annoying because there's a lot of names for the same things. Perpendicular vectors are also called orthogonal vectors. So like just like I'll put it like again, I'll try to put both name like phrases like side by side. So I'll write perpendicular in parentheses orthogonal. So perpendicular is also called orthogonal. Also, it's called orthogonal. So so in a way, the dot product, what happens is that it's related to perpendicularity because the moment you compute the dot product and you get 0, that means actually that will tell you that the vectors have to be perpendicular, and that actually ends up being a very useful thing to have. Yeah.
Would the zero vector be considered perpendicular to?
Right, it's kind of like extreme case, but yeah, you can call it perpendicular to everything. So it's kind of like the old, but you know, usually, yeah, when I compute the dot product, it would be for vectors, both of which are not a zero vector. But if you wanted to include a zero vector, then yeah, you can call it perpendicular to everything. It's kind of like a bit weird because it doesn't have like a direction or anything. So it's kind of like you know, not like a big thing whether you want to calculate as perpendicular or not, but it's just more convenient to call it perpendicular to everything. But yeah, but at least if both have a non-zero length, which is usually what we'll care about, then yeah, like then this kind of like looks like the way you would expect it to look. And is that okay? Okay, so the first reason is the dot product matters because it tells you if the vectors are perpendicular. In fact, it tells you a little bit more. This is less important because it also tells you something when the angles are acute or obtuse. So if you I don't know if you remember this thing, but if the angle is less than 90 degrees, like so here, like the angle is between 0 and 90 degrees. So that's called like an acute angle. This is an acute angle. So if you remember, like cosine is positive between 0 and 90. So what would happen is that if the angle is less than 90, the dot product will be positive, which is kind of what happened in this situation, right? Like the angle was 45 degrees and the dot product ended up being positive. So here the dot product is positive. And if you have something like this where you know, like the other possibility is for the angle to be, you know, between 90 and 180. So this is called obtuse. So when the angle is between 90 and 180, you the thing is like cosine is negative for those values. If you remember like how the cosine of theta behaves, so the dot product will be negative. So in fact, from this, what I'm trying to say is that from the sign of the dot product, you can figure out whether the angle is exactly is less than 90, more than 90, or exactly 90 degrees. So, yeah. Okay, let me show you this more as an excuse. To show you GeoGebra because it's not like a super like interesting application, but it's like a nice thing to give you like an idea of how you can use GeoGebra. So again, like GeoGebra is kind of like a Wolfram Alpha, but more like geometric. So you can type something like that product here. And it just gives you like, like, you type that product and see what your options are. There could be some better ones. Okay, this one is kind of nice. So, like you have these two vectors, U and V. They are giving you here, like they're giving you the lengths of each vector. They're showing you the angle between them. And you kind of start playing around with it. So like here, like the angle, the dot product happens to be 0.31. The number itself doesn't matter too much. It's just like it's positive, it's kind of reflecting the fact that, the fact that the angle is acute. So, if you play with, you move one of the vectors around, if you like, then like it's showing you different values for the dot product. And then you kind of, try to get it perpendicular and you see that the dot product is diminishing in value until you get to exactly 90 degrees. Well, I don't know if I'll get it to 90 degrees in this animation. Like, okay, so there's a 90-degree angle, and then you keep moving it around, and it becomes negative, right? Because the angle becomes obtuse until you get to 180, right? And then once you get to after 180, okay, so this animation like really keeps using like the bigger. Like that's kind of, I mean, the angle should always be taken between 0 and 180. So this animation is like a little bit off in that case. So it should have been with this other angle. So unfortunate, but at least from 0 to 180 it kind of works like the way it's supposed to. So yeah, like in this animation, actually, the way we are defining the angle, we would have used this angle, so it would have become positive again. But so let's just ignore that. But at least you can see kind of like playing with the vectors around, like how the dot product changes. But for now, like we're just looking at the fact that it became 0 exactly at 90 degrees, and it was positive for less than 90 degrees and negative more than 90. That's all that matters so far of what I've said. Okay. But so yeah, like the nice thing about GeoGebra is like, you just want to, sometimes you just want to try something out and find an animation. And so you just like enter the name, and most of the times you'll find something relatively useful. So. Oops. Okay, and then okay, so this is the first reason why the dot product matters, and the other reason why it matters is it's also an extreme case, which is what happens if you do the dot product of a vector with itself. So actually, I don't think I need the display anymore. Being annoying once. So what's the dot product of a vector with itself? So let's say I want to find u dot u. So in a sense, like what that means is like just make a copy of u and place it on top of itself, right? So I'll just draw it like kind of parallel to it, because if I draw it literally on top of itself, then you cannot really distinguish it. But just imagine that you copy pasted u and just move it a little bit upwards, so like you can really see them as like two of the same vector. And so if you look at this, it's like the product of the first vector. Sorry, the length of the first vector times the length of the second vector, but now the two vectors happen to be the same, times the cosine of the angle, right? But then what's the angle between a vector and itself is just 0, right? So you put cosine of 0 is 1, so that just gives you the length of the vector squared. That's, which is nice. So what that means is that there's another way to think about it. which is that the length of the dot product is let me put it like in a box as well. If you take square roots on both sides, what that tells you is that the length of a vector is the square root of the dot product with itself. Okay. Okay, I'll show you how that works in a second, but we do need an extra property of the dot product. But what I'm trying to say is that the dot product can be used to detect if two vectors are perpendicular, and it can also be used to find the length of a vector. Okay, but before actually putting this to use, I just need to tell you something else about the dot product, which is another property that it's assumed to have, which is just like the distributive property. So So here, what does that mean? I'm trying to take the dot product between a vector and a sum of two vectors. Okay, so it's useful always to compare these things to what happens just with ordinary numbers. So the analog of this with ordinary numbers, right? Let's think about what I would write with like just like numbers. Right, like if they were just numbers, I would write something like U times B plus W. What you would do in that case is just like distribute like or FOIL it or whatever. So like you would just put like write this as UB plus UW, right? So that's what you would do with numbers. The point is that the dot product kind of allows you to do the same. So you kind of do UV and UW. It's just that now, before in the middle, you wouldn't put anything. Now you put dots because we're taking the dot product. So the only difference like between, the situation with numbers and the situation with vectors and dot products is that, you just keep the same symbol in every step. So if it has like a dot on the left-hand side, there should be dots on the right-hand side. That's basically it. Okay. Okay, so let me give you an application of all these things so that you can see how this works in practice. So let's. So this is like a more like this is like an interesting example actually. This is kind of like the type of things that like like a typical like exam problem or something like that. So this is something nice. So of all these properties. So imagine that I give you a vector. I'm going to give you a vector u. I don't know what, like what the vector is, so, but I know that the length of u, let's say that the length of u is 2. I mean, obviously there's some units implicit here, so it could be 2 meters, 2 feet, 2 miles, whatever, based on whatever units you're using. And then I give you another vector with the length of v being 3. Okay. And I tell you that the angle between these vectors is let's say 60 degrees, which is pi/3. Okay, so a question could be to find the length of u plus v, just with this information. With this information, find the length of u plus v. So just to clarify, like if you remember last time, u plus v is a diagonal of the parallelogram, right? So I'm telling you, you have these two vectors. Let me just draw them like this. This vector has length 2. This other vector has like length 3. Actually, look a little bit. I should make this one smaller. Actually. This one has length 3. Right, you could complete these two vectors into a parallelogram if you wanted. And so what this is asking for is the length. U plus v corresponds to this diagonal. So actually what this problem is asking you is what's the length of the diagonal if you know the lengths of the sides of the parallelogram and the angle between them. So what this is asking is for the length of this diagonal. And we don't know anything else about the vectors. So we only know their lengths and their relative angle, the angle between them. And that should be enough to figure out the length. Now, the way to do it, the idea is that the way to do it is just using this property, and this property. Okay, so all the solution actually comes from using these 3 properties together. Okay. And now, just to kind of because this usually causes confusion, let me call W the sum. So we're trying to find the length of W. So this is going to be unfortunate that the board is kind of small, but okay, so I want the length of this vector. So we have 3 boxes, 1, 2, 3. Which of the 3 boxes is related to the length? The second one, right? Like the second one is directly about the length of a vector. So let's start there. Okay. I guess it is. So what I'm saying is that the length of W the length of a vector is the square root of the dot product of the vector with itself. So that's important to remember. Okay, so I'm just applying that property for the sum. Okay, so like I'm just using the second property here. But what is W? W happens to be U plus V, right? So let me just put here square root of u plus b dot u plus b. Is that making sense? And then, okay, what happens here? Again, you should compare this to u plus b. Like imagine if I had given you u plus b times u plus b, right? Like just for numbers, not vectors. So what you would do is like FOIL it, right? So you just do the same, but you just start putting like a bunch of dots everywhere. So. Let me see. Good. So you do this one with this one, you get u dot u. You get this one with this one, you get u dot b. You get this one with this one, you get v dot u. And then you do this one with this one, you get v dot v. So you get 4 things, right? Does that make sense? And once you get to this point, you can almost start substituting everything. But again, we just have to apply this formula a little bit more. So u dot u is just the length square of the vector. So let me put here length square of the vector. V dot v is the same story, but it's the length square of v. So the first and fourth terms in this sum is just like length squares. Okay. Well, I don't think I have said it so far, but you know, u dot v is the same as v dot u, because you're multiplying the lengths and times the cosine. So like is a like, you know, the formula doesn't really change. So maybe I should put this like 2 times u dot v. So let me just explain, like clarify this, since u dot v equals v dot u always. So that's important to know also. Okay. And we're almost there, because what's the length of u squared? The length of u by assumption was 2. So you get 2 squared. What was the length of b squared? B like had length 3, so you get 3 squared. And then you get 2 times the dot product. What is the formula for the dot product? It is the product of the length and the cosine of the angle between them. Okay, so that's why we needed the cosine as well. So you get 4 plus 2 times length of u, which is 2, times length of b, which is 3, times cosine of 60 degrees, which is, what is the cosine of 60 degrees? Is that 1/2? Yeah, good. So it's 1/2. Perfect. And then 3 squares left. Okay, so you get 4 plus 9, that's 13. And then these 2. Okay, so you get 6, right? 6 plus 4 is 10. So is that like the square root of? I think they should all give you square root of 19. So what that means is that this diagonal has like length equal to root of 19.
Yeah, this is just an observation, but u squared plus v squared plus 2ub cosine theta is like the law of cosine.
Right. Like actually, yes, like you know, this is also another reason why the dot product is defined in this way, because secretly is like a hidden way of like working with the law of cosines. So like the law of cosines is kind of like a tricky law to memorize. You never have to memorize it if you just know how to apply the dot product. It just comes like every single time, it would come naturally when you start foiling things out and things of that sort. that making sense? So that is, this is like when you look at this problem, the first time it's kind of confusing how to attack it because, you only know that, like, you don't know like the specific entries of the vectors. That's what can be a little bit confusing. So you don't know the coordinates of the vectors. You just know their lengths and their and the angle between them. But if you just work with the properties of the dot product, then it is possible to still solve the problem. So we're almost done with the time. So what I'll explain next time is that there's an alternative way of computing the dot product. I'll explain next time how this formula appears, but it's kind of like at least useful to write it down. So what I'll tell you next time is this formula, which is very useful and this is like in practice how many times you compute the dot product, but definitely something like this is like a very common exam problem. Like you'll see some of the workshop, which are just like a bunch of things like this. So what I'll tell you next time is why this formula works. This other formula works. So next time, what I'll explain is that if you have two vectors U and V, let's say you have a vector U, which has like entries U1, U2, U3, and a vector V, which has entries V1, V2, V3. So the idea is that U dot V what we will find is that U dot V is what you get if you multiply the corresponding entries. So you would do like. So if you multiply the first entry with the first entry, the second entry with the second entry, and then the third entry with the third entry. Which is kind of what I was saying is the naive multiplication, but the difference is that now they are not entries of the vector, you just add them together. So the difference, it kind of ends up being the case that the product can be found in this way as well. So I'll explain next time how that works. Basically, what we will do is write this everything in terms of ijk, and then you do like a mega foil, and it just pops out. So, but again, like it's kind of just keep it back on your head. But I'll tell you next time how that works. Okay, so yeah, I'll see you on Wednesday. You have the presentation on Thursday, right? Yeah. Okay, sorry. So yeah, Thursday, the recitation problems will be, workshop problems will be on this product stuff. But we'll just do some 20 minutes next time on this.
Yeah, yes, I was.